Hello everyone, welcome to Reactify Labs. Today we will talk about chain replication. Okay, so chain replication is basically a data replication strategy kind of thing. Okay, so we have to uh, maintain data replication, right? So that our system becomes fault tolerant and some other reasons as well, right? So that's why one of the strategies for that is chain replication. Okay, so before we start, let's discuss the structure that we are going to follow today. First, we will talk about the introduction of chain replication. Next, we will go to the detailed mechanisms of how chain replication works. Okay. After that, we will see the advantages of chain replication strategy. Then we will see the challenges associated with chain replication strategy. And then we will see examples of some systems which use this strategy. Okay. So chain replication, as the name suggests, is like this. There will be a chain, right? And it's just like any other system, any other chain that you can see in your daily life. Like the in your school, there was a line for prayer, right? That is also a chain kind of thing. Why replication? Yeah, we will talk about that. But that is also a chain. Any queue can be considered a chain in real life if you see. In factory, if you see the assembly line, that is also a chain. So that's it. Nothing different from that. Okay. As I have told you before, if any word resembles something in your daily life in computer science, it must be it. Okay. So this is what we do. We have our nodes in a chain format. And why? So that the data can be replicated across all the nodes. But the question is, why in the chain format? We will see that in detail when we discuss the technicalities of it. Okay. That said, let's start. Okay. So first, introduction. So chain replication is a robust method for managing data replication across distributed systems, thus ensuring consistency and reliability. It leverages a sequential arrangement of nodes to propagate and confirm data writes efficiently. Okay, it's a robust method basically. What is it? So, robust method for managing data replication. For managing data replication across distributed systems. Across distributed systems, thus ensuring consistency and reliability. Consistency and reliability. Okay, so basically we are managing data replication, right? It leverages sequential arrangement of nodes, means nodes one after the other, to propagate and confirm data writes efficiently. Okay, let's talk about the detailed mechanism, and here we will know how it works. Okay, detailed mechanism. So first step is, let's see the node structure and their roles. Node structure and roles. Okay, so there is a head node first of all. So it's like this. If there are multiple nodes, so if you start from here, there will be a head node and there will be a tail node. Okay, head node and tail node. So basically there will be a head node first. Head node is also called a primary node. It receives incoming write requests, processes them, and initiates propagation through the chain. It maintains a local log of write requests, handles client acknowledgements, and manages network communication with intermediate nodes. Okay. Next comes intermediate nodes. Intermediate nodes. These nodes. Okay. So these intermediate nodes forward write requests to the next node in the chain and update their local state. Each intermediate node has a local write log, handles write propagation, and ensures proper ordering and consistency of write operations. And next is tail node. It's the final node in the chain which processes the write requests and serves read requests. It sends acknowledgements back to the head node, and it maintains the most up-to-date data, processes read queries, and ensures that data is synchronized with preceding nodes. So any write will happen at this node. Okay. And since other nodes are replication, it means, since other nodes are replication, it means what happens is a data which is present in one node will be present in other nodes as well. Okay. So the write will first come here. The write will only happen at the head node. Okay. When the write comes here, it propagates the write to the next node, which propagates to the next node until it reaches the tail node. Okay. So all nodes have the data. So all the write goes to the head node. Okay. Let me write it in a good handwriting. Yeah. All the writes go to the head node and all the reads go to the tail node. Okay. So read happens from the tail node and write happens from the head node, right? Why? Because if you see, write is fine. It can happen at the any end, but it happens at the head node, because if write happens here, okay, then it goes at this one, then it goes at this one. Okay, let me change the color to explain it better. So write happens here, then it comes here, then it comes here, then it comes here, and let's say it failed here. Okay, in that case the data is inconsistent, right? So it means any write which is this one, this write, it's not consistent. It's not consistent across all nodes. So what was consistent across all nodes? What is consistent? The write which was which happened last before this, and the one which reached here. So if there was a write which reached at this node before the before this one, it means that tail node is updated. It means if the write has reached at this node, it means all other nodes have that write, right? So that is the actual most recent consistent value. That's why write goes here and read happens at this end, because if something is present at the tail node, it means it is present at all the nodes, right? That's why it happens, read happens from the end, and write happens from the front, because it has to send, because it needs to make sure that all the nodes receive it, right? So basically it's like anywhere from the write happens. It's not that this is head and this is tail. Like anywhere where the write happens, for example, let's say if I write here, this will become the head node and this will become the tail node, right? It's just that you have to read from the head node and write from the tail node. Okay. And whenever a write I think I said something else. You have to write to the head node and read from the tail node. Okay. And the intermediate nodes, they are used to store the writes and propagate the writes to the next nodes. Okay. So read from tail and write from head. This is the gist of this chain replication strategy. Okay. Now let's talk more detail about it. Okay. So let's talk about now the write operation in detail. Okay. Second is write operation. Write operation. So the head node receives a write request with data and metadata. Metadata like the timestamps or version numbers. The head node logs this request in a local queue to ensure it can be retried if needed. Okay. The head node updates its local state or database with the write request. The head node then sends the write request to the first intermediate node. This involves serializing the request data and sending it over the network. Okay. Then intermediate nodes, what intermediate nodes do is they receive the request, log it and process it according to their local queue management policies. Okay. Each intermediate node updates its local state. Okay. Then the updated request is forwarded to the next node. This may involve network communication and serialization. And when it finally reaches the tail node processes the request, the write request, updates its state and writes it to its local data store. The tail node then sends an acknowledgement back through the chain to the head node, ensuring all nodes in the chain are updated. It means when write successfully reaches the tail node sends an acknowledgement that yes, this write has reached to me. Okay. So the head node can send the next write. Okay. Each node along the chain receives the acknowledgement and confirms that the write request has been processed. This ensures consistency and integrity of the data. Now all nodes know that, okay, this write has been a successful write. Okay, there is no inconsistency in the system now. Next is handling busy nodes and queuing. Handling busy nodes and queuing. Okay, so first comes queue management. Queue management. Each node has a buffer with a defined size for incoming requests. If the buffer is full, new requests may be delayed or rejected. Nodes use FIFO policy, FIFO as in first in, first out. FIFO policies to ensure requests are processed in the order they are received. Okay. And next is back pressure mechanism. Back pressure mechanisms. So nodes may implement something called rate limiting in order to control the flow of incoming requests and prevent overload. If a node is overwhelmed, it may shed load by rejecting or delaying some requests with mechanisms to retry later. Okay, so if there is an overload, they can either do the rate limiting, like, okay, we will not accept any requests now, and along with that, if there is too much load, they can do the load shedding also. Okay. Next comes load balancing and scalability. Load balancing and scalability. Okay. So the system can dynamically adjust the number of intermediate nodes based on the load. For example, adding more intermediate nodes can help distribute write requests more evenly. Okay. System may use multiple chains to balance load, with different chains handling different set of requests. Okay. Next is, in some systems, hierarchical chains are used where a chain of nodes feed into another chain, allowing for complex load balancing and redundancy, right? So there can be multiple chains as well for effective load balancing. Okay, and there can be like hierarchical also, like this chain feeds into some other chain. Okay, like if this request is processed, only then this request will start. Okay, so that's it. Next is fault tolerance and recovery. Fault, FAULT, tolerance and recovery. Okay, in case of node failures, what happens? Nodes use heartbeats or health checks to detect failures. If a node fails, the system needs to identify and reconfigure around the failure. Failed nodes can be bypassed by adjusting the chain configuration or using alternative routes. Okay, let's say this node fails. So what happens is the connection will be automatically established between these two nodes. Okay. After a failure, the system may need to synchronize state from other nodes to replay logs to ensure consistency. Failed nodes that recover can be integrated into the chain, and the system must ensure that their state is consistent with the rest of the chain. Okay. Let's talk about some of the edge cases as well. Edge cases. So long network latencies between nodes can impact the performance of write operations. Techniques like batching or asynchronous communication may be used to mitigate this. Systems may use optimized network protocols or data compression to reduce the impact of latency. Like if you see this, if the chain is small, then writes can be fast. But if the chain has become too long because of the increased load, too many loads means too many intermediate nodes needed to be added, then the write can become slow. Okay. So to handle this, some of the optimizations need to be done, right? And in case of network partitions, the system must handle scenarios where the parts of the chain are isolated. Techniques such as quorum based decisions or partition aware algorithms can be used. Okay. So for example, again, like I gave you in the beginning, each worker node, okay, each node can be considered a worker node. Okay, each worker performs specific tasks, okay, and passes the partially completed information or the write request. Basically, if we take an example of, let's say, daily life system called, let's say, assembly line. Okay, assembly line of a machine, or let's say truck. we make a truck, okay? Then each worker performs specific tasks and passes the partially completed product to the next worker, okay? Let's say this one made the steering, this one made the window, this one made the tire, this one made the door, this one made the gear, something like that, okay? Each worker performs specific tasks and passes the partially completed product to the next worker. Buffers between workers ensure that the line runs smoothly even if one worker is slower, okay? So between the workers there are some buffers also, right? So that even if some worker is slow, that's fine. Like slow is temporarily, right? So if there is a temporary slow, it means there is some space where you can store that partially completed product, and that can be processed as soon as the worker gets the bandwidth, okay? Similarly, let's say there is a kind of like, let's say, document approval workflow. For example, in your office or in your school, some approval needs to be taken. So that document, that's a write request, okay? Consider that document as a write request. A document goes through a series of approvers, right? Let's say first your manager approves, then director approves, then senior director approves, then the VP approves, then the MD approves, then the CEO approves. This kind of flow is there, right? So that request goes through a series of approvers, each adding their input. And if an approver is busy, let's say the director is on leave, the document waits in a queue until it can be reviewed and passed along. If the director is on leave, it cannot be passed to the VP, right? Or the senior director, because it needs to be handled at that time. Unless it's permanently down, it will not be diverted. Like, let's say if this is your flow, your manager, director, senior director, VP, MD, and let's say this is the CEO, okay? So if, let's say, director is busy, the request will wait in a queue, right? But if this director has left the organization, in that case, what happens is, until the new director comes, the manager will report directly to the senior director, right? So this is what happens in the chain management also, or chain replication also. So now let's talk about the advantages of chain replication. Advantages. First one is consistency. As you can see, chain replication guarantees that all nodes eventually have the same data due to the linear propagation of writes. Okay. Next is scalability. Scalability. It enables the addition of more nodes to handle increased load and improve performance. Okay. Once the load increases, we can add more intermediary nodes. And fault tolerance. Fault tolerance. It provides redundancy and recovery mechanisms to handle node failures and ensure continuous operation. By the way, there is one thing I think I missed. So let's say there are nodes. This is a head node. This is a tail node. What if head node goes down? In that case, any other node can declare itself as the head node. Okay. If the order is like this, like I'm showing it like this, it's not generally like this, right? There is not a connection. It's just what you can say, virtual connection that I'm showing. Okay. The order is defined, but there is no connection. So any node can declare itself as the leader, and this can be not the leader, this can be head. Okay. Or let's say if this node is down, this node can become the head. So the connection will be like this now. So from here, the request will go here, and from here it might come here. This will be down. Okay. Like this. Anything can happen. And similar thing can happen if the, let's say, tail is down. So if tail is down, again, somebody else will become the tail. Okay. This is one fault tolerance mechanism that is followed in chain replication strategy. Okay. Now let's see the challenges. So first one is latency. As I said before also, as the length of the chain increases, the latency will increase, right? Write operations may experience latency due to propagation time through the chain and queuing delays. Next is head node bottleneck. Head node bottleneck. So the head node can become a performance bottleneck if not managed properly, especially under high write loads. Okay. And complex reconfiguration. Complex reconfiguration. Managing node failures, reconfigurations, and maintaining consistency can be complex, and it requires careful handling, right? Now let's talk about some of the real world examples of systems which use this chain replication strategy. Okay. First one is Microsoft Azure Storage. Microsoft Azure Storage, particularly the Azure Blob Storage Service, uses a variant of chain replication called lease-based chain replication. In Azure Storage, data is replicated across multiple storage nodes. When a write request is received, it is first written to the primary replica, which is the head of the chain, then propagated to the secondary replicas, middle of the chain, and finally acknowledged once it reaches the last replica, which is the tail of the chain. This ensures that all replicas have a consistent view of the data. Okay. This approach provides strong consistency while also achieving high availability and fault tolerance, just like chain replication. Okay. Just like what we studied in the chain replication above. Next is LinkedIn's Voldemort. LinkedIn's Voldemort. LinkedIn's Voldemort is a distributed key value storage system used for large scale data storage. Voldemort experimented with chain replication for its high availability storage engine. In this setup, updates are passed down a chain of replicas, with each replica passing the update to the next one until it reaches the end of the chain. Only after the last replica in the chain acknowledges the update, it is considered complete. Right? Chain replication in Voldemort aimed to provide high throughput for read heavy workloads while ensuring consistency across replicas. Okay. Google file system. Next is Google file system. So the Google file system, which is like the Google's large scale data processing systems, they use replication strategy that resembles chain replication. In GFS, Google file system, each file is split into chunks, which are then replicated across multiple chunk servers. When a chunk is written, the update is sent to the primary chunk server, which is the head of the chain, and then passed sequentially to secondary chunk servers, forming a chain until all replicas have the latest version of the chunk. This approach again helps Google file system maintain strong consistency while ensuring high availability. Okay, so these were some of the examples of the systems which use this strategy. There might be more, but for this lecture, these three are enough. So maybe you can study and you can try to do some research to see what all other systems are there which use this strategy and why they use this. Okay. So we have always studied that, okay, our system is strongly consistent or eventually consistent, high consistency, low availability, low consistency, high availability. So now you know, if we say something is strongly consistent, how that strong consistency is achieved, right? So yeah, now you can talk about this also. If somebody asks you in the interview that you said the system will be strongly consistent, how will you make sure that it's strongly consistent? You can say that one strategy is to use chain replication. Okay. So yeah, that's all there was in this video. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.